I will be speaking about, again, Brunn Minkowski. You heard a little bit yesterday. It will maybe be a little bit annoying, but there will be some new things, hopefully, into this talk. So let me just say first, okay, this is a joint work, ongoing work, which we haven't finished, and we started almost 3 years ago. So it's a bit long. So it's a joint work with Mathieu Fradelisi and Olivier Guédon from Paris-Est. And right, so let's first say what is my goal here. First is I will be working on the sphere mainly, and I would like to present you a spherical localization. Emmanuel yesterday talked this, the whole week he will speak about localization, and his version is a 1D version. Mine will be a 2D version, and it's actually very, very good for us to keep and compare everything which I would do today with what Emmanuel also will be doing. And the Gedenken would be if we could actually prove what I will prove today with a 1D localization. I can't do it, but maybe you guys, and maybe all week after this talk, we could learn some more. So, and then, wait a second, where's the other side? The second part is I want to convince you that our understanding of Brunn Minkowski theory on Riemannian geometry, and at least, Riemannian manifold in general, is very meh, in the sense that not cool, not good. And I will tell you why. I mean, there are many, there are very great theorems, which I will discuss, but still, we are not there. And I want you to understand, I want us to understand today why. And the third point would be, this side. Okay, the third point would be I will present an example, which will be a theorem for this, to show you that, it's not really cool. At the moment, we lack of a good Brunn Minkowski theory, at least on the sphere. So the past, I would say, 1.5 years, I've been doing other things. So maybe since mathematics grows very fast, maybe somebody came up with a breakthrough and I'm not aware. If you know it, please let me know. But as far as I know, anyways. So let's start with our good old friend, Rn. We all love it. And let's just remind a few cool things on Rn, which probably will be annoying for you, but anyways, I have to do it. First theorem is Brunn Minkowski. So again, Emmanuel told us yesterday, but I will be saying this. So let lambda be between 0 and 1, and x, y be two bounded measurable sets, such that 1 minus lambda x plus lambda y is also measurable. Be aware of pathologies here, because there are objects which are bounded and measurable, but this guy is not measurable. But anyway. Then volume of power 1 over n is greater than or in other sense, you can tell that the function of volume power 1 over n is concave on the set of bounded and measurable sets of Rn. Yes, cool. Oh yes, x plus y, like again Emmanuel taught us yesterday, is this guy. And again, this is super Euclidean. When you take something and you add something to it, it's a Euclidean operation. Okay? Now, so the proof of different proofs of Brunn Minkowski. One is, Millman's yesterday's proof from yesterday. localization 1D. 2 is what again Emmanuel told us. You prove your Brunn Minkowski for boxes. Boxes are objects which have a face which are actually parallel to coordinate axes, and you add these guys together, and you prove Brunn Minkowski for these guys, and then you do approximation. I don't like very particularly this proof, but people do use it anyways. And the third one, which is the more I would say the more famous one, is from Prekoppa-Leindler. Prekoppa-Leindler. So Prekoppa-Leindler tells us the following: you have again lambda between 0 and 1, and you have f, g, h, 3 non-negative function in Rn, integrable, right? Such that for every x and y in Rn, you have f of lambda x plus 1 minus lambda y is larger than, attends, qu'est-ce que je fais? H, who cares? Fx power 1 minus lambda and jx power 1 minus lambda. If this inequality is satisfied for every x and y, then an integral of h in Rn is larger than integral of f in Rn lambda multiplied by integral, maybe I can go up, yeah, g in Rn. A log concave version of Brunn. Pardon, yes, y. Sorry. Thank you. Sorry. Okay, so from Prekoppa-Leindler, you apply for indicatrice or characteristic functions to sets, and you get the Brunn Minkowski, the log concave version of Brunn Minkowski. Then you use homogeneity in Rn, which again, homogeneity is super Euclidean. Okay? And then you can prove that guy with this. So this plus homogeneity gives you Brunn Minkowski. The proof of that, again, Emmanuel will probably tell us, and you will learn about this much more from Emmanuel. But it's with induction and 1D transportation, optimal transport. At least one of the proof. And then there is another proof of Brunn Minkowski which is very beautiful and is due to Borel and is with heat flow. So at time 0, you have a tree function which satisfies this guy. Borel can prove that at time t, pt of h, pt of f, and pt of g still satisfy this guy. So when you go to infinity, this tends to integral, and then you get Prekoppa-Leindler, and again you get Brunn Minkowski. It's fantastic and absolutely beautiful. That's it. Okay, so yesterday Nicola told us something very, very important. He said, if you want to have a theory of Ricci flow, or Ricci curvature on, say, weird objects, once you define this for weird objects, you have to also see that these weird definition of yours coincide with the good definition for like normal objects or smooth manifolds. It's the same with Brunn Minkowski. If you want to define a Brunn Minkowski theory for some manifolds, we have some expectation from Brunn Minkowski. We want that it satisfies a few things. So what does Brunn Minkowski give us? At least a few things that I would tell you, not everything. The very what Brunn Minkowski gives us. The most, maybe I would say the most important one is Brunn Minkowski very nicely and easily gives you isoperimetry. In the sense that you can prove the isoperimetric inequality in Rn just applying Brunn Minkowski, and I think again Emmanuel will talk about this. So I'm not going to concentrate on this isoperimetry today, which, sorry? No, sorry. And the second one, at least, is Covariogram. Brunn Minkowski gives you Covariogram, And this is what I am going to concentrate today. So what is Covariogram? It's very easy and very, very funny. Theorem. I hope my butt is not showing. Okay. Anyways, so let K and L be two convex sets, two convex bodies in Rn, right? Then the function gkl of x, which is equal the volume and dimensional volume of the first one intersected with the translation of the second one, right? Power 1 over n is concave on its support. You understand? So you have a convex set, and you have another guy. You move it. You translate it, right? And then you look at the volume of this intersection, and then you say, this Covariogram tells you that this guy is power over 1 over n is concave when on the support. Proof? Well, obviously Brunn Minkowski in 2 lines, and so observe that K intersection. Do you see? No. Yeah. L plus 1 minus lambda x plus lambda y. This guy is equal K intersection L plus. Attends. So not do a mistake. Yes. K intersection 1 lambda x plus lambda L plus y. Okay? And this contains 1 minus lambda K intersection L plus x plus lambda. I will tell you what geometrically this means. And then you take Brunn Minkowski for this guy. It tells the volume of this is larger than 1 minus lambda volume of this plus lambda volume of this 1, and this is bigger, and then you get the Covariogram. Sorry? What it doesn't make any sense? This guy plus sorry, what is this? They play x with, sorry?
X with x plus L, probably.
Yes. Yeah, well, anyway, the point is you get this guy, you do this plus this, and it's contained in this guy which is in the middle, and then you apply Brunn Minkowski and you get this Covariogram very easily. Anyways. So now, after this very short introduction on Rn, I like to go on Sn. Okay. So, what do we know on Sn? Do we have a Brunn Minkowski? Well, yes, we do. And it's due to, well, let's go on Sn. So Sn is just the Riemannian with the canonical Riemannian metric such that the sectional curvature of this guy is everywhere equal to 1, or if you want, is the boundary of the unit ball, as you wish. So, we saw that Prekoppa-Lindler gives Brunn Minkowski. So in order to have a sort of Brunn Minkowski, it's natural to ask if we have a Prekoppa-Lindler. And yes, we do have a Prekoppa-Lindler. And this is a theorem of Cordero. And later on, Cordero, McCain, and Schugen, I never learned the name. And these guys also extended this Brunn Minkowski on Riemannian, every Riemannian manifold. And I also believe that Sturm is also did some Brunn Minkowski on Riemannian manifold. But anyways, I'm just going to say the theorem of Cordero. So let's, again, alpha is between 0 and 1. F, G, H, 3 integrable function on Sn for every xy in Sn. You take z, which is alpha x plus 1 minus alpha y. I tell you what this guy is. If we have h of z is larger than a function of on the distance of x and y, power n minus 1, which I will tell you what this function is. Then you have integral of h over Sn is larger than integral of f power alpha integral of g Sn 1 minus alpha. So first of all, what's this? Well, again, you take x, you take y, you take the geodesic between x and y, and you take the point which satisfies this guy. Okay? And what's L alpha? Well, L alpha is the following. It's a function for alpha 0, 1, theta, which is the distance, which is between 0 and pi. This guy is equal S theta divided by S power alpha, alpha theta, S power 1 minus alpha, 1 minus alpha theta. And S theta is sine theta divided by theta. So when the distances are extremely close, this guy goes to 1, and this we get locally the Brunn Minkowski on Rn. Obviously, things get harder when the distances get large. So because due to the positive curvature, actually, we have this function here. And the proof of Cordero is in 2 pages, very beautiful, and also with optimal transport. And actually, this is sharp. I don't think that we can do for this definition of distances, z, I don't think we can do better than this. This is actually a sharp inequality, I think. So obviously, once we have this, we can have a Brunn Minkowski. You have a set x on Sn. You have another set y on Sn. How do we define alpha x plus 1 minus alpha y? Is that you take a point here, you take another point here, you take the geodesic, you get this point. But you do this for every 2 points, you get another set in this, and then you would know that the volume of this is larger than, again. But it's a bit harder because you will have this, but anyways. So the question is, okay, we do have this precopaline now, but does this give us the isoperimetric inequality on the sphere? And no. And does this give the Covariogram on the sphere? And the answer again is no. And why the answer is no? Well, let's see. Very simple. Draw a geodesically convex set on the sphere, okay, which is this guy. And now let's take epsilon, which is very, very small ball here, inside S, and let's take a geodesic and move this epsilon ball on this geodesic, such that for every point, the ball stays inside the convex. Now you want to define Cordero's. What will this plus this be? It will be a bigger ball, right? So what Cordero will give us is that this bigger ball is bigger than whatever. But we all know that this ball, I mean, it has to, the equality has to be better than that. There's something better than this. You know, this is that's why what was. There's actually this question was a question. All these motivation come from a question of Gromov. I will tell you later. But yeah, you see, if you want to apply that, you just don't get the basic basic equality. So what do we expect? And that will be our theorem. Guédon, Padelizi, and me. So S, open convex set on Sn, sigma, a geodesic segment contained in S. Okay? So let's take a point on sigma. So you have sigma, which is in S. Let's take a point here on this sigma. And for every epsilon, we have volume of S intersection bar of radius epsilon intersecting your convex set S power 1 over n is larger than alpha volume S intersection bar x1 epsilon power 1 minus 1 over n plus 1 minus alpha volume again S intersection b x1 epsilon x1 x2 1 over n. What is x1 and x2? x1 and x2 are point x2 and alpha is in 0 1. So okay, I take a point x1 and I take another point x2 and I take alpha only on this geodesic, I take the point which is alpha x1 plus 1 minus alpha x2, and now I draw my picture of epsilon radius balls and I do the intersection with the guy and I take the volume of the intersection and it satisfies this type of Brunn Minkowski. That's why I call this the talk of today Brunn Minkowski type inequality, because this is a Brunn Minkowski type inequality. And as far as I know, I mean, I don't think I even asked Cordero. I mean, he doesn't know how to prove this theorem using his method of optimal transport. However, at the end of this talk, if I will have, Jesus Christ, what, I'm done? Okay, Jesus Christ. What the hell? Yeah, okay. Oh, yeah. I thought it was on 9. All right. Thank you, God. I had a heart attack. Okay, so at the end of this talk, I will tell you a method of maybe proving this theorem with optimal transport. However, I myself cannot do it because I'm rubbish at optimal transport. But you guys probably can do it. If I just tell you how, I mean, maybe you will. But at the time when we discussed, okay, so I was talking, we were talking with Gromov, and he was telling me, we were talking about nothing to do with this, but he was saying that, you know what, take this guy, this is obviously larger than minimum of this, between the minimum of the volume. He was saying that the volume of intersection in the middle is larger than the minimum of these two guys, okay? And he thought, and he wrote it somewhere then, and he said that this is obvious, right? And I said, definitely it's obvious. And I was in the metro, I was thinking, this is definitely not obvious. And I just pray that he doesn't ask me how to prove it. Because, you know, and then I discussed with the Olivier and Mathieu, and we end up, you know, it became a serious business. But at first it was all the motivation, and that's how I got involved with Brunn Minkowski. So obviously we will want to prove this theorem with using localization, and that's what I'm going to do. And we'll give you the sketch of a proof. The proof is long and super annoying at one part. Oh no. But at least the ideas, I want you to understand the idea of the proof. The idea of the proof goes back to Gromov and Millman, 1987, in a very interesting paper, which they use the localization. And then later on, Simon Aleskerk writes a nice paper, short paper, reproving what they prove, but in very, very nice details. And obviously, Cannon, Lovac, and Simonovich also use this localization to prove isoperimetric type inequality regarding convex sets in Rn. And Gromov again used localization to prove a waist theorem on the sphere. But he used a k-dimensional, larger dimensional localization. And well, we also see that now localization, with what Emmanuel is teaching us, we see that localization is proving a lot of things. So, okay, the idea of the proof sketch again goes back to sketch. Anyway, idea goes back to Gromov and Millman. Right. So let's first working with alpha equal 1 over 2, because this function, obviously, the function m epsilon x, which is volume of the ball radius epsilon intersection s power 1 over n, is continuous. So in order to prove the concavity of this function, it's enough to prove the mid-concavity. So it's enough to prove for alpha equal 1 over 2. So we're going to concentrate only on the midpoints. This way we get rid of the alpha and everything. Right, so the proposition, the first proposition, Gromov, Millman. This is nothing new. Honestly, this proposition is just Gromov and Millman copy. But the idea is very funny. There exists either S2 in Sn. All right, so the dimensions is larger than 3. By the way, for Ni equal 2, okay, just think about it wherever you will have a little bit of time, and just think about how you can prove this for N equal 2. And that's even not an easy thing. It's really annoying. Trust me. The reason, which is I will come back again, but even if for n equal 2, it's funny. So we assume n is larger than 3. We will have to come back to 2 again, but for the moment, n is larger equal than 3. So there exists either a S2 in Sn containing the point x3. So x3 will always be. So I have this geodesic inside S, which is fixed. Nothing is moving. So S is fixed. My geodesically convex is fixed. Sigma, which is seated inside S, is also fixed. And my point x1, x3, and x2 also are fixed. Maybe you don't like my notation. You would prefer this to be x1 and a half. But I'm just writing it x3. Okay? So everything is fixed for the moment. Nothing is moving. And epsilon is also fixed. And you have these 3 balls, which are of equal radius, okay? And you take this volume, and this volume. Right, so there exists a S2 in Sn, which contains x3, which contains this midpoint, and a measure, which I will have to define this, but I will define this during the proof, a probability measure actually, nu2, defined Wait a second. Where am I? Oh yes, on S2. Such that so for simplicity, I note ui equal S intersection B xi epsilon, right? So there exists a measure nu2 which will not be the Riemannian volume, probability Riemannian measure if you want, the nu2, such that nu2 of u3 intersection is S2 divided by the measure, no, I can break this up instead of sitting. Measure of u3, this is equal mu2, u2 intersection is 2 divided by measure of u2, and this is equal mu2 u1 intersection S2 again divided by mu of u1. So either we have this guy or we have a geodesic. Now let's notate this kappa, again containing x3 and a measure nu1 on kappa, such that, again, this is verified, but you replace mu2 by mu1, and you replace S2 by kappa. Okay? So I can write it if you want, but maybe write it here, such that mu1 of, I will tell you what this means, but let's not panic for the moment. Equal, voila, okay? Or there exists, we can also reach a Dirac measure in some cases, but if you have a Dirac measure, then obviously the inequality will be obvious because the Dirac power 1 over n is larger than Dirac power 1 over n plus Dirac 1 over n divided by 2. But so I can only concentrate on 1 and 2. So, as again Emmanuel told us yesterday, the idea of localization is to reduce the dimension, but obviously you have a price to pay. The price to pay is that you no longer work with nice measures. You have to work with more complicated measures. And this is what I put the measure here. Oh, Jesus, sorry. So, and well, the point is to obtain these guys, and also to understand what these measures are. Once we have that, then we are good to go. So far, any questions? Is it understandable? Do you understand what I'm saying, or it's going too fast, too slow? Is it okay? Exactly. Exactly. Or again, yeah, exactly. We have, okay, so I'll tell you again what is. So I have S2, which cuts the 3 sets, and it captured these measures. Or I have S1, which will cut again this 3 set, and capture again this measure. And that's all. For every Sn larger than 3, these guys exist. And it's super, super, super fun. Yes? No, I want epsilon to be outside of the S. I actually want that. Otherwise, what's the point? I want epsilon to be as large as possible, and anything you want. That's the whole point of the thing. Yeah, it's just equality. It's a concept. However, once again, be aware, my inequality, I will tell you again at the end, is even in this case is not sharp. And I will tell you why. And it's obvious why it's not sharp. So I have what my my feelings towards this, my theorem, our theorem, is sort of like Freud's feeling for Vienna. It's a sort of love and hate. Because, on one hand, I like my theorem, but on the other hand, I think it's pretty still useless. Because still we are far from what the nice theorem will be. And I will tell you at the end. But it's cute. Papa. So prove. Right. So let's, this is very fun. So let's define a map from Sn to R3. So it takes a point. Right, so look at the point, a point on X as a vector, Euclidean vector, which takes the point 0 of Rn plus 1, and it goes towards X, okay? Now, this vector defines an oriented hyperplane. Do you agree, right? And now this oriented hyperplane will cut the sphere in two hemispheres, right? So I take my point X, and I define the map which will be, right, and also I normalize the Riemannian volume. So the Riemannian volume on the sphere, the measure on the sphere is equal to 1. And I denote that Riemannian measure by mu. But if you like, you can still use volume here. So X takes, the first coordinate will be the measure of mu1 intersecting this hyperplane, which I denoted like that. See? So you have a point X, this goes there, and defines a hyperplane. But then this intersection will, this is n-dimensional. It's actually a hemisphere oriented by this hyperplane, right? Anyway, so I take the measure of mu1, my mu1, intersection with this hemisphere, right? The second coordinate will be the measure of mu2 intersection the same hemisphere. And the third coordinate will be the measure of mu3 intersection the same. Okay? This is a continuous map. You agree with me? Just you turn this and the volume, it turns very continuously. Now apply the very fun theorem of Borsuk-Ulam. Borsuk-Ulam tells you there exists x and minus x on sphere such that fx equal f minus x. But if we have fx equal f minus x, what does that mean? Then we will have this equal measure of mu1, mu I intersection x, this hemisphere is equal of measure mu I, the other hemisphere. Right? You agree? Actually, it's mine. Yes. Okay. And that means I'm having measure of mu I intersection x hemisphere is equal 1/2 measure of mu I. So I'm finding, using Borsuk-Ulam, what I'm doing, I have these three sets. Okay, well, they're sitting somewhere in S. So I cut this in two parts such that the measure of this guy is equal to the measure of this guy, the measure of this guy simultaneously. Okay, the measure of this guy is equal to this guy, and the measure of this guy. And this always can happen due to Borsuk-Ulam, thanks to Borsuk-Ulam. Right? So now I take that part which contains the point x3. So x3 is either there, is either down, or is in the boundary. If it's in the boundary, I take one of each. I don't care. Now, I continue the cutting. I do the same thing for, say, this guy. But I'm not going to write all the procedure because the time will. So I cut again this part, such that, again, this measure will be equal to this measure will be equal to this. This again can happen due to Borsuk-Ulam again. So I redefine a new map. So I will have a sequence of maps such that the solution will be the halving, basically. Since I'm dividing the measure of mu I in each step in I 2 power I, at one point at infinity, I have to reduce the dimension. The dimension goes down. So now I'll find a lower dimensional sphere which contains the point x3, right? And which will satisfy these measure things. Now, if that dimension is larger than 1, 2, because I can define a new map from Sk, which goes to R3. So if k is equal to 1 and 2, I obtain the proposition is finished. Right? I guess I get a measure on that and I'm done. Now, if k is 3 or 4 or 5 or 6, I still can define this Bohr-Circular map because this is larger than 3 and there will be always a solution. So I keep doing the same thing until again reducing the dimension. If I get 1 and 2, done. If not, I keep doing. It's very, very not rigorous, isn't it? You don't like it. But okay, that's the reason why Mathieu and Olivier, they are able to give a very rigorous sense to this thing using functional analysis. So what they can do, I mean, and they did that very, very beautiful papers. They wrote about localization functional analytic by saying that the extremal sets of some measures are even, studying the extremal sets of some class of measures, and that is equivalent to this thing. What I like geometry more. I will give it to you. So it's Olivier, Guédon, and Mathieu Pradelizy. It's a very beautiful. Actually, they have two papers about this localization. This way was done exactly the same way by Gromov and Millman, and also I believe Canon Lovász-Seminovic did also with this hubbing procedure, if I'm not wrong.
Yeah, but you say something about rigorous. I mean, so unless you're really going to clarify the measures really detailed with that paper, and certainly
yeah, Alice also.
Paper certainly super rigorous.
Yeah.
All these papers are in our hands except for the Gromov-Millman.
Yeah, I agree that is, but I mean this induction going to infinity, I mean maybe it's a little bit scary. However, I believe that is also quite rigorous. But anyways, this is the idea, and it works, and is so once again you use the Bohr-Circular map to cut your sets, dividing by 2 until you reduce the dimension. If the dimension is larger than 3, you keep cutting, and if you get until you reach either 1 or 2, you can, or 0. 0 is fine, but you and then the proposition is okay, is proved. Okay, so that's fine. We can cut and obtain. We can reduce the dimension, but what is that measure, which is in the theorem in proposition? So that's what I will talk about now. The measure. We cannot do better than that. Because, we don't stop. We are obliged, we cannot do, because if we stop, because we can obtain, say, needle, 2-dimensional needle, right? Once we cut, we can reach dimension 2. But after that, we cannot reduce dimension 2 to 1. Because S2 to SR3, Bohr-Circular doesn't apply, So that's why I asked that it's very interesting to keep in mind after the lectures of Emmanuel, maybe we would be able somehow to use a 1D localization, which I have at the moment I don't know, but it's very, very, I don't know if we can. With this method, with our method, we cannot go, we are sure that we will either stop at dimension 1 or 2. So, yes, what are these measures? How do we get more water? I have to, yes, this, like this, yeah? And I have to wash this, like, carefully? No? Like, yeah. Thank you, sorry. Yeah, that's much better, sorry. So it turns out that these measures are absolutely continuous with respect to the Riemannian volume. They are probability measures, and actually they have really nice concavity property. due to the positive curvature of the sphere. And this was what, I mean, I think Cedric Villani also used this kind of measure somewhere. But I learned it from Gromov, at least. That's what, let's say, prudently, let's say it this way. This kind of measure. But again, I think Millman and Gromov, they knew these kind of measures before, but they just didn't use it. Until Gromov wanted to prove the waist, and he had to use these measures. So what are these measures? It turns out, okay, so definition. Function first. A function f from Sn to R, or let's say supported, if you want, on a convex set, but it's probably not necessary. But anyways, is called sine power k concave if the restriction on every geodesic is a sine k concave function. So we are turning this definition into a one-dimensional definition. And what does this one-dimensional definition mean? Now parameterize your geodesic, canonically with blah. It means that for every... Alors, attends. No. I have it. Yes, of course. So it has to satisfy alpha between 0 and 1 for every x1, x2 on the geodesic parameterized. We have to have f alpha x1 plus 1 minus alpha, they use it? Yes. X2 power 1 over k. I put sine power of k because I want the concavity behavior of the function resembles the function sine power k of x. But many people like sine power 1 over k because I take the power 1 over k anyways. That's not really the issue, hopefully. This is larger than sine of alpha, the distance between x2 and x1, multiplied by that, divided by sine of distance of x2 minus x1, f of x1 power 1 divided by k plus sine of 1 minus alpha x2 minus x1 divided by sine of x2 minus x1 f of x2 power 1 over k. Particular interest is when alpha is equal 1 over half, then you will get f of x1 plus x2 divided by 2 power 1 over k is larger than f of x1 1 over k plus f of x2 1 over k divided by 2 times cosinus of the distance of x2 and x1 divided by 2. So this is better than concavity because we have this here, right? That's thanks to what? To Sn. So when this, okay, so it turns out that that measure that I wrote on the proposition will be a probability measure. Yes, very good question. It means that if power 1 over k satisfy if equal g, it means g. And the equality holds for the sinus, cosinus, and their linear combination. Very good question. And okay, so where just a funny example tells you that these functions are super natural. Is that let's be in R2, okay, and let's take S1, right, and let's concentrate on this part. So S1 plus, which is this guy here, and let's define the function x on R2, which is equal y power k. Okay? Now takes the restriction of this on the sphere. That will be the function f theta, which is, it will be equal sine, is it sine or cosine? Sine. Sine theta power k. So, the function, the sine k concave functions are the xk concave functions in Rn, which are homogeneous when you take the restriction on the sphere. So they're supernatural. But when you write this on the sphere with the geodesic distance and the spherical distance, these weird terms appear. But that's actually good for us because it's better. Anyways. Right, so it turns out on that proposition that I wrote, which is disappeared now. Everybody is okay with this function? Okay, right. They're not very, they're supernatural, fun. Okay. No. Stop time. It's horrible. Okay, so it turns out in the proposition when I wrote the measure, entre guillemets, I meant, so back to the proposition, right? So I had two cases. The first case was the S2, you remember, sorry, S2, and that measure, which satisfied that equality, the tree equality. The second case was the kappa, and the measure on kappa, right? So what is this measure? It turns out, Gromov, that this measure is a sine, okay, is absolutely continuous with respect to dV of S2, if you want the Riemannian volume of S2, and the density is sine power n minus 2 concave. So we reach dimension 2 from n, we get n minus 2. Here, we reach dimension 1 from n, we get sine power n minus 1 concave. Though, we can go a little bit further than that, but I'm not going to go now. We can actually prove with localization that these guys are sine n minus 2 affine, which actually they will be exactly the combination of exactly the function sine plus cosine. But that requires a little bit of more geometry and more than just that proof that I gave you. But it happened, it's true. And that very beautiful trick is used, I learned it from Canan Lovac-Simonovich, very beautiful. The same argument can work for this for the sphere because you can actually use the Euclidean localization, add a homogeneity there, and get the dimension 2. Or you can get it from Mathieu Olivier Guédon and Mathieu Fradelisi by this amazing functional analytic way that they do. But you still get the affine, but I don't care here. Let's just assume that they're concave. Affine is that this equality is equal. This is equality. Or if you want them to be smooth, they will, this differential inequation happens as to be an equation. And also, if you want the solution will be a plus sine theta plus theta 0, power k plus b cosine theta plus theta 0 power k. Or you can just reduce this and take that. Just that. Okay? So they will be like this. Okay. So now let's just, now we reduce the dimension. So we either have a zero-dimensional problem for that for which it's set, the problem, or we have a one-dimensional problem. Let's prove the theorem if we get to the y dimension, because that's the easy part. I'm not going to prove it, actually. No. It's going to be, so the one-dimensional problem will be just, you don't even need this sign concavity. These guys are also 1 divided by n minus 1 concave, since I said they're better than concavity. And then you just use what Emmanuel yesterday taught us, Borel, Braskamp, and Lieb inequality, which, shall I quickly write it? Shall I? Yeah, let me do it. Borel, Braskamp, Lieb says Prekoppa-Leindler, okay, the same thing as Prekoppa-Leindler, but you have this, quickly, you have this K concavity. So you have a function which is 1 over n minus 1 concave and satisfy this guy. Actually, why do I put alpha? Always 1.5 would work. Would work. Divided by 2. Divided by 2 for every x and I now on your geodesic kappa. This is satisfied. It's just a one-dimensional, it's just a Euclidean thing. Then the integral of h power 1 over n, the dimension is 1 plus n minus 1 is larger than integral of f power 1 divided by n, 1 plus n minus 1 plus integral of, this is g 1 divided by 1 plus n minus 1. This is 0. So you get the n-dimensional, the n-concavity of the theorem if you get the one-dimensional needle. It's just Borel, Braskamp, Lieb. If you get the two-dimensional needle, that will be a whole mess. You will have to prove a theorem which will be the same Covariogram that I wrote, S geodesically convex on S2. Now, S2 is no longer a Riemann, doesn't have a Riemannian volume. It has a sine power n minus 2 concave probability measure. Okay? Then, the measure of mu 3 power 1 over n, I think it's n minus 2 if I'm not wrong. Yes, it's n minus 2, is larger than the measure u1 1 over n minus, no, it's n, sorry. It's n plus measure and divided by 2. So the same Covariogram, but for this sine concave probability measure should be true, but the proof is super annoying and messy. Why? Because we have to use spherical geometry because we do not have any sort of functional inequalities which would just quickly give us the result. So we actually have to write by hand things, and it's very messy. And so far we have been trying to understand whether we could actually find a sort of Prekoppa-Leindler which would directly give us, at least for dimension 2, but we still are, we don't know. Okay, so that goes for this. Sorry, it was vague. But let me just tell you how my idea of proving this guy, I'm very curious if you guys can do it, actually, because that would be super awesome. Okay, so first thing, this inequality is not sharp. Our theorem is not sharp. Why? I tell you why. So you are in S2, okay? You take a geodesic, and you take your delta positive, and you take a tube around this geodesic, okay? This tube will be S1 plus delta. This guy is not convex, geodesically convex. It's mean convex, but it's not convex. However, our inequality is for this case is sharp, because for any epsilon, any ball that you get, and you move around this tube, this geodesic, these volumes will be constant. So you have the equality. So our theorem is not sharp. The sharp case is this case, and which is not geodesically convex. So, and if it's not geodesically convex, if we do the localization our way, maybe Emmanuel, with Emmanuel's methods, maybe we can do better. But in our way, because we are cutting convex set, at the end of the day, we don't know if we get a geodesic inside this guy or not, you know? So localization with our method will not prove the sharp, at least, will not prove the sharp case. On the other hand, that's just for the balls. Who cares for the balls? What about the other more fancy convex sets? You know, if a Covariogram has to be true for fancy sets, convex set. If you get whatever in Rn, again, even if you want to use the localization, you will not prove it, because once you cut, the symmetry will go. The geometry at each stage of the cutting will change. You know, balls has this property that for each cutting you still get a ball, but if you get another, you know, so this. A localization, at least in our way, will just, like I said, I'm Freudian about it. But, so still something is missing. The reason I believe what is missing is because we are not looking at the right concavity. The right concavity is not this 1 power divided 1 over n or this log concave on the sphere. The right concavity is much, much deeper than that. And I think it's, I have some sort of idea, and I do have a conjecture, and I do have a definition for the Minkowski sum on Riemannian geometry, but I have no proof, so I'm not going to talk about that until I can prove something. Then I can get invited again, maybe present as a good thing. However, last thing, sorry, how to prove this with theorem with optimal transport? So the idea, this is the idea which I was talking to some people, is the following. So you have a convex set, and you have a geodesic inside, okay? Take the normal bundle to this geodesic set. What is the normal bundle? It will be a cylinder which will contain your sphere, right? So a cylinder is you can wrap it up, it becomes the plane. So now project these, your guys, pull it back on the normal bundle. These are balls. They will remain balls. The distance will just be it will maybe differ, but who cares about the distance? We are looking for volume. So you bring this on the normal bundle, which will be the cylinder. You get, and the convexity is preserved, actually. Okay? So you get a convex set in Rn cylinder with 3 balls. So you are in the set of the Covariogram. Only thing which differs is the measure. The measure will be super weird. So can we use the Brunn Minkowski, optimal transport for that measure on that set? Did you get it? Because I'm curious if you can prove it. So you have the normal bundle. You pull back your shape. You draw it nicely on your cylinder, which is basically, and then you pull back the measure. You don't care about the distance. The balls will be the balls, and then you prove a Covariogram for a convex set on the normal bundle with optimal transport. That's it. Cheers. Sorry. Emmanuel. Go ahead. No. Sorry again. Thank you. That's it? Okay, ask a question. Go ahead. Maybe people will be curious. What? Yeah. You said you can. Okay. Yeah, for me too. Thank you. What is it again? Say it again. Yes.
In all cases, whether it's one-dimensional, two-dimensional, it satisfies curvature dimensional parameters n minus 1 that's what the sphere satisfies.
So it will always be n minus 1. So you don't get the n minus 2 concavity or whatever.
No, you do because in 2 dimensions that's what it translates to.
Ah, that's what it translates.
The property is called CD n minus 1n. That's what sphere satisfies, and that's what any localization on the sphere, whether it's 1 dimension, 2 dimension, whatever dimension it is, maybe it's constructed.
For me as well. Thank you.
And the second thing, regarding your conjecture of what's the right concavity, right? So if you believe that the two-dimensional case certainly looks, problem to analyze. But if you believe that the answer will be the same as in 1 dimension, then when you did the 1-dimensional analysis here, then you forgot about the sine n minus 1 concavity, and you passed 1 over n minus 1 concavity, then applied whatever, Minkowski, Brabant, something. But you can just look at the paper for Minkowski.
Yeah, but
Then they have the version of, the Borel-Brascovic version with the right.
But I believe actually that in dimension 2 is not what you get in dimension 1. It's very different. Okay. That's exactly. And actually, I can tell you.
In the 1-dimensional case, you get even a sharper concavity than what you showed.
Sure. Of course. In 1 dimension 1, I have.
And that will be the conjecture.
No. I think in dimension 2, my understanding of the thing is, if you want, I can give you what I believe. The concavity is given. I mean, the right conjecture for Brunn Minkowski is the following. R3 is larger than R1 plus R2 divided by 2. What's that? So you have 2 objects, okay? You define the Brunn Minkowski sum in some ways, and you get the third one. Now, you get, for the first one, you get a ball of radius R1, which is this guy, which is equal to this, the volume. And the second one is a ball of radius R2, which in Rn, which is equal, the volume is equal to that. The right Brunn Minkowski on the sphere is just simply this. It tells you that R3, whatever it is, the ball of radius R3, which gives the same volume, is just larger than this 2 divided by 2. And this is this in my, and so the concavity is given by the integral of sine of n minus 1 from 0 to something, which will be equal to the volume of your thing. So it's very, very different from in dimension 2. I think that's my conjecture, but it might be wrong, or it might. But however, if you have that, you will get isoperimetry, and you will get my theorem as well. So, but this is what I can't. So I know that, but I cannot. I mean, anyways. And also, what is the? I can define the geometric Brunn Minkowski sum, but that's going to be too long, anyways. So I think you see that the right concavity in dimension 2 is super different from at least in dimension 1. At least, I mean, as far as I understand. Anyways, thank you. Thank you. So let me. Sorry for taking longer.